My life has oscillated through several things. I'm in a superposition of several states. In the physics state, during 1973 to 84, I was at Indian Institute of Technology, Delhi, where Love Grover of the famous Grover algorithm did his bachelor. Over there, I did my PhD in theoretical plasma physics, and thereafter I taught several subjects, including quantum optics. But then I changed because life is a superposition of several things. 84 to 2004, I worked in engineering, in energy and telecom companies, in engineering and management roles. And thereafter I got unemployed. So I had to switch to something else. I happened to be at the Florida Department of Revenue, where I was tax auditor, from physics to tax auditing. And currently I'm SAS developer. SAS means Statistical Applications System. Now, and this is heavily data centric. And why I got interested in quantum optics is because as tax auditor we process data. Fraud detection is a big thing. And I realized that quantum computing has a big need in fraud detection. That's how I got interested in quantum optics. And quantum physics had already intrigued me 50 years back when I learned quantum physics from Feynman lectures. And this year, 2024, happens to be 100 years after Bose published his Bose statistics, and Pauli published his exclusion principle. Okay, so let's connect the dots. Quantum computing relies heavily on the linear superposition principle and quantum entanglement phenomenon. These two are the cornerstones on which quantum computing rests. So understanding the basics of these two things is very important. Unless we clear our fundas for these things, quantum computing progress will be hindered. And if we understand these fundamentals very nicely, we can do better progress in quantum computing. Now, this linear superposition principle and quantum entanglement phenomena, they rely on states and measurements. So, understanding the concepts of states and measurements is key to the whole thing. All right. Now, states can be spatial or temporal. They can be structural or behavioral, reversible or one way or irreversible, discrete or continuous, periodic or aperiodic. So these are different categories of states. Reversible states, awake and asleep, because you can be asleep and later on you can be awake. So these are reversible states. On the other hand, alive and dead, these are irreversible, one-way states, right? So these are the, different kinds of states. States can have parent-child relationship. Alive states, children are awake and asleep states. So these are the states, right? Basic understanding of the states. Measurement types. Measurements can be terminal or intermittent, primary or secondary, destructive or non-destructive, discrete or continuous, periodic or aperiodic. Now terminal, so electrons at the screen in a two-slit experiment is a terminal measurement. But if we track the trajectory of the electron while passes from the source to the screen, it's an intermittent measurement. Primary measurement, seeing whether a cat is alive by opening the cage in Schrodinger's cat experiment, is a primary measurement. But on the other hand, if you detect whether the cat is live or dead by measuring the sounds from the cage, is a secondary measurement. So these are primary and secondary measurement types. Now, linear superposition current principle, current interpretation. Current interpretation is heavily probability based, right? So it focuses only on the terminal destructive measurement. The linear superposition as interpreted currently focuses only on terminal destructive measurements and is silent about intermediate and non-destructive observations. It does not say anything about the intermittent and non-destructive observations. It assumes that a system has no meaning until measured. And this is the crux of quantum mechanics. It says that system has no meaning until measured. This is the current interpretation. It cannot explain why a measurement gets only a Bayesian states. We say that when we measure, we get a Bayesian state. It does not say why we get that Bayesian state measurement. It fails to explain the quantum entanglement principle. So if you take the linear superposition alone, current interpretation, you cannot explain the quantum entanglement as it happens. So I'm proposing another interpretation. I'm giving a new interpretation for linear superposition principle. A quantum system oscillates among its possible reversible states. So what I'm saying is there are several possible states and the quantum system oscillates between those possible states. And this is wave-particle duality in a way. So what the the proposed interpretation is an extension of the wave-particle duality. Wave-particle duality is only for a particular spatial position. But what I'm saying is that is possible for all other kinds of states. So the interpretation which I'm giving is an extension of the wave-particle duality, and I'm saying that a quantum system oscillates among its possible reversible states. That's the proposed interpretation. In equation of the Bayesian, quantum state, in terms of Bayesian states, the product of Hermitian conjugate of the coefficient with the coefficient itself is the fraction of the time that particular Bayesian states. So what does that coefficient mean? That coefficient means that how much time it will be lying in that particular state. So that's what the coefficient means. Cj is a 1 for time between this and this when it is on, when that state is on, and 0 otherwise. In most cases, the cycle time is so small, the measurement sees a random Bayesian state depending on when the measurement is taken. So why do we see the random state? Because we take our measurement at random time. Let me explain this. So let's say, 12 hours you are asleep and 12 hours you are awake. An alien guy from somewhere else outside the solar system visits you at a particular point and sees that this particular person is asleep. He goes away. And then several years later, at some random time, that particular lands on the to your bed again and sees that you are awake. So he might say, oh, this person is a sort of randomly awake or asleep. But no, what happens? You are going through that cycle of awake and asleep. The why you are seeing that random is because you are taking those measurements at random time. So randomness is not because of that, but the source being in the random, but because you are taking those measurements at random time. So this is the crux of the proposed interpretation. So you are transferring that randomness from the object to the measurement, who takes that measurement. A quantum system appears to be random or probabilistic because randomness or probabilistic nature of timings in measurements. Right? So this is the proposed interpretation. So let's explain this. So for example, let's say spin x of electron, right? So 0 and 1 are, for example, two possible states of the electron spin. So that spin keeps on oscillating between 0 and 1. Initially it might be at one particular frequency, fixed frequency. Later on it might be a growing frequency, but is a good pattern. And some other time it might be completely random. So that electron spin, for example, oscillates between 0 and 1. It may be with a fixed frequency, or it can be a growing frequency, or it can be random frequency. So these kind of oscillations, right? Now, oscillatory spin. So if it keeps on rotating like this, then it has a fixed speed. But if it goes like this, then it has 0 and 1, so oscillations. So oscillatory spin is pendulum time. On the other hand, fixed universal uniform unidirectional gyroscopic spin versus bidirectional pendulum time spin. So this is the oscillatory spin concept. Quantum entanglement phenomenon. Personally, I feel that Schrodinger gave the name entanglement in a bad way. He should not have given the name entanglement. That's what has created the big problem about quantum entanglement. It's a mystery, right? And as many people know, quantum entanglement is mysterious, but it is mysterious because of this name. Personally, I feel that Schrodinger should not have given this name entanglement, because when entanglement, it says that these two particles are somehow connected, or they are communicating, or something like that. What John Bell said is entanglement, the performance part. So he said that entanglement says the correlation between the quantities. So Bell's interpretation interpreted quantum entanglement in terms of correlations. When the two particles with 0 and 1 states are not correlated, you will have the terms of 0, 0, 0, 1, or 1, 0, or 1, 1, 4 terms. But when these two particles are entangled, correlations are 0, 0, or 1, 1. So instead of 4 terms, you have 2 terms. So that's the quantum entanglement. And that's what John Bell suggested. But this John Bell's interpretation is silent about the physical basis of quantum entanglement. It's the performance aspect. It says what happens when the entanglement occurs. But it does not say why quantum entanglement occurs. Right? It does not solve the EPR paradox. Right? Spooky action at a distance. It does not resolve that, because it does not explain why quantum entanglement occurs. So we have to give some other interpretation. And if we understand that linear superposition proposed interpretation, it directly gives that quantum entanglement new interpretation. It says that when two particles are ejected from a common source, their physical quantities oscillate synchronously with respect to each other. That means those oscillations are synchronous, and that's why those, you see that kind of quantum entanglement or correlation, right? So entanglement is because correlation because of the synchronous oscillations of these quantities. So for example, if you have 3 electrons, electron A, electron B, electron C. A and B are oscillating at the same frequency in phase 1. At those points, in those phases, those two electrons, electron A and electron B, are entanglement. Why? Because their spins oscillate at the same frequency. Now in phase 2, both electron A and electron B have growing frequencies for the oscillations, but they are growing differently. So they do not have oscillations. And then in the fixed random pattern, they are not also. So electron A and electron B are entangled because they oscillate at the same frequency. Now, how to validate this quantum entanglement new interpretation? It can be easily interpreted. Experimentally verified. What you can do is you measure those polarizations in the regular setup and do the Fourier analysis. And if you find that those frequencies are discrete, then you will say that this new interpretation is valid. So it is possible to experimentally validate this interpretation. Now, once you have these, new interpretation for quantum entanglement, you can understand that it's possible to have emulated quantum entanglement and new ways of quantum computing. So with this new understanding of quantum entanglement, you can devise new ways of doing quantum computing. For example, Grover had suggested an emulated quantum computing based on pendulums, right? But pendulum is not that great a way and not efficient, but he suggested that it is possible to have quantum computing with pendulums, right? So what I'm saying is with this new interpretation, it's possible to have various ways. So here is one way. You can have microwave channels and which are synchronized, and those synchronized channels, you can shift them through some CRT kind of shifter, and you can have that quantum computing based on microwaves, coherent microwaves. And instead of laser, visible radiation, microwave might work better. That's what I understand. Then what I have done is I have developed Excel file, XLSM file, and Python package for simulating quantum computing. So I have developed this quos package, Python package quos, and they are on my GitHub repository under quos and PyP quos packages. So with those you can simulate. There are several simulators, but the simulator which I have made has certain advantages. It's easy, it's simple, it's compact, and it can be easily transferred. So what you do in Excel method, you just take this, copy this XLSM file, and on the top, the spreadsheet, you write down those gates, and then run QA macro, and it can give you gate plots, loss pairs, and probability pairs. Similarly, for quos package, you just import the quos package, write the string defining the circuitry of the quantum computing, and run this QG text. It will give you the plot. So it's easy. So it is very portable. So this is the quos package which I have developed. Thank you so much. Thank you.